Let's take a look at the Physics C equation sheet, but not this one. This one, the math sheet, which means calculus, also vector products and trigonometry and other stuff, but we're interested in calculus, but not from this sheet. Rather from this one, an older one, last used way back in 2014. Let's compare the two. They both start out with the chain rule, but I don't like the way they state it. More on that later. The equations are a lot alike, but the newer sheet has a bunch of A's in it. What's that about? Check out video number 2. These 10 equations are really just 5 equations and 2 concepts. My goal for these videos is to make these 10 equations seem less like a group of strangers and more like an interconnected team. Derivatives. This is the power rule. Get used to this one. And integrals as inverse operations. Inverse operations, they undo one another. Add 3, subtract 3, multiply, then divide, square, and take the square root. Inverse operations. We integrate and we differentiate, which is clearly seen when y equals e to the x, because it is strangely its own derivative, and therefore its own integral. And it gets a bit worse when you include the a's like the current equation sheet does, but not much worse, and the natural logarithm, taking the derivative or integrating. We will leave sine and cosine for video number 3. Time to get to the graph. Notice that the axes are asymmetric. That's to be expected. We do distance versus time or force versus distance graphs here. This isn't a math class. Okay, maybe it is a little bit. Differentiate. df dx equals f prime of x. Integrate. Integral of f dx equals, capital F of x. Function number 1. Find the derivative with the power rule, and there it is. It tells you the slope. At x equals 0.5, the slope is 3/4. At x equals 1, the slope is 3. At x equals 1.5, the slope is 6.75. Derivative achieved. Next, integrate with the power function 2.0. What's that? This. Great. But what's that? It's the function whose slope is x cubed. Everywhere the slope of capital F is equal to little f. Get it? And it also tells you the area under the curve between these two limits, and it works. Each rectangle on this diagram here is about a half of whatever. So this is a 1.25. Great. But you're talking derivative, integral, a function with a value, a slope, and an area. But you said derivatives and integrals are inverse operations. And then you said that the derivative gives you the slope and that integrals give areas. So you're trying to tell me that the function is the area of the slope or the slope of the area, and that's crazy. Crazy or genius. Like this new graph, it gives profits every day for my lemonade stand. And what do we mean by profits? Profits are money earned per day for these 20 days of lemonade selling. And you agree that the area under the curve, right? You agree that the area under this curve is the total cash I squeezed out of the business. Sorry for that one. Things started out slow. I only made 50 cents on my first day, but after a couple weeks, I was raking in almost $4 a day. Early on, profits were growing fast. It seems here we are nearing market saturation. Profits are still increasing, but just barely. One more time. Profits nearly doubled from day 2 to day 3. That's good news. But my bank account was hardly moving. Profits stagnated from day 17 to 18, but my piggy bank burst with all those quarters. I graphed my daily profits, a value. The slope of the graph tells me how much my value was changing. Thank you, Mr. Derivative. Again, the value I was graphing was the money earned per day. The value I was graphing was the rate at which my wealth changed. The money earned per day. See what I'm saying? I boldly affirm the ridiculous, that the value of the function really is the slope of the area, and vice versa. Moving on to the next curve, the parabola. Its slope is 2x, meaning that its slope here is 1, 2, 3. Find the integral. 1/3 x cubed, because if you differentiated that, you get x squared, and the integral gives you the area under the curve between these limits, which is a little bit more than 1. Next curve, a straight line. Let's find the slope, and you could use this, although you don't really need to because the slope is 1 everywhere. What about the integral? 1/2 x squared. And the area under this graph is exactly 1, otherwise known as these two rectangles. Good. Next, line. Y equals 1. A flat line, a boring line. Slope equals 0. What about the integral? Same equation. We're on a roll. The area under this curve again equals 1. The next curve is, hey, it's a curve again. Let's find the derivative. -1 over x squared. That means that the slope here is -4, -1, and -4/9 here. Exciting! Integrate. Truly exciting. It's impossible. See that? You're trying to divide by 0. That's an error. You weren't allowed to do that. Or is it an error? Looking at the curve, it does have a well-defined area between those limits. So what's the problem? What's going on here? Who remembers the answer? We saw it earlier. Anybody remember the natural logarithm to the rescue? Our hero. But that's exactly my point. This function wasn't created as some special case patch for the power rule. There really is a good reason why the natural logarithm equals integral of 1 over x. And we'll get to it in just a moment. First, one more function. 1 over x squared, and its derivative, -16, -2, -16/27, I think. And the integral, this time the integral works. And there is our area. And that, honestly, is about as much fun as anyone ought to have with the power rule in one day. Two other functions to talk about, though. E to the x, which is pretty amazingly boring, and the natural logarithm. These two functions, of course, know one another. We talked about the derivative and the integral as inverse operations. Well, so are exponents and logarithms. They undo one another. And both of these lines go to infinity. E to the x gets there much quicker. But they are reflections of one another around the y equals x line. They are inverse functions. And notice also the absolute value for the logarithm. We are only currently accepting natural logarithms for positive values of x. Thank you very much. Our job is to show that the slope of the natural logarithm really should equal 1 over x. And I'll buy it. I'll buy it because the slope is really big here, just like 1 over x is really big when x is very small. And the slope is small over there, just like it should be. But let's prove it. Inverse operations. Raise e to that power and differentiate. Note that e to the ln x equals x. They undo each other, I told you that. And finally, our chance to use the chain rule. E is its own derivative, but don't forget the dy dx part. One final substitution and we're done. If y equals ln x, then dy dx equals 1 over x QED. And finally, ready to find the area. Well, you survived part 1, see you for part 2.